PI would like your feedback on it, see how well it works. So if you liked it, don't like it, whatever, let Stephanie, the conference coordinator, know. Send her your comments, or maybe just tell her. Anyway, this week we're pleased to have Erik Verlinde. He got his PhD in Utrecht, did a postdoc at IAS, and then had faculty positions at CERN, Utrecht, and Princeton before landing in his current location of the University of Amsterdam. He won the 2011 Spinoza Prize, and today he's going to tell us about string theory, entropic gravity, and the dark universe.
Thank you very much. Thank you also the organizers of this conference to allow me to speak here at this colloquium for all of you. Indeed, I think we are living in some exciting time where we are seeing connections between information theory, quantum information, and gravity, and a new way of thinking about gravity is starting to appear. And what I like to explain in this presentation is that I believe that this is going to solve some problems that we have with understanding gravity, not just at the short distance scale where we usually think that quantum gravity is important, but really solving issues about the dark universe. That means understanding properties of dark energy and of dark matter. So I will try to convince you of that, and indeed I will show some connections and some explicit comparison even with data. It grows out of combining ideas of string theory and insights from black holes and things that I just started developing some years ago, which are called entropic gravity, and it ties in very nicely with recent developments in ADS-CFT. And this is sort of the idea that starts to arise, is namely that gravity is indeed emergent. We should not think about it as something that should start from the beginning as being assumed to be there and described, say, like a Lagrangian of the type of Einstein's action. We really should think about what space-time is made of, and then this quantum information connection becomes important. And then gravity is sort of a consequence of understanding space-time itself. So black hole thermodynamics is an important hint. Actually, it's the first thing that people found where we have some clue of a connection between gravity and entropy and information, therefore. String theory has done a lot, actually. It has explained the Bekenstein-Hawking formula by microstage counting. It has shown us different ways of thinking about degrees of freedom. String theory is not just about strings, it's about D-branes, and it has all kinds of different phases even where we can represent degrees of freedom in different ways. And here I use the phrases Higgs and Coulomb branch, and I'll explain a little later in the talk what these words mean. And then ADS-CFT, the holographic correspondence between gauge theory and gravity. And there it's the connection with entanglement entropy that has been recently sort of studied and been very actively sort of seen as a way of deriving gravity even from this information theoretic point of view. There are connections, but there are also differences in these ways of looking at it. And indeed, there are also puzzles. I mean, there's the puzzles associated to horizons have not been completely solved. There's the information paradox, and now the recent version, which is indeed based on quantum information theory, which is called the firewall paradox. It really starts to question whether space-time exists beyond the horizon, or whether we should think about horizon regions as really something else, or that something else is happening to space-time than in our normal surroundings. And this also connects to de Sitter space. De Sitter space has a horizon, and therefore it is, prone to the same kind of issues as we have for black holes. There's also the cosmological constant. I mean, we have to understand this long-standing problem. The cosmological constant problem is not something that we have fully understood, although I think in ADS-CFT we have maybe some ways of understanding it. Finally, there's the dark universe. I mean, we have puzzles. We have dark energy, dark matter, and in this talk I want to sort of convince you that there are connections between understanding emergence of gravity and space-time and what is being seen in dark energy and dark matter. I'm going to be quite explicit. I mean, I'm going to indeed tell you what I think the microscopic model should look like. I'm going to also present a formula that's going to describe phenomena that we are observing. And it has to do with understanding the scales of dark energy. Dark energy has a scale set by the cosmological parameter, the Hubble scale. And of course, it's not set by the Planck scale. This is the well-known problem. So the fact that the universe has two scales, the large scale and a short distance scale, is an important clue to what is going on. And this difference is actually set by understanding the amount of quantum information in our universe. So this is the beginning, sort of where the first clues came about black hole being different and also gravity being different. Black hole thermodynamics. It's the first law of a black hole where we know that the change of the mass can be related to the change of its area. And this is then connected to the first law of thermodynamics by identifying the area with entropy. And the temperature then becomes equal to the surface gravity of the black hole. One way of sort of deriving this is by writing down the familiar relation that the escape velocity at the horizon should be the speed of light. And that gives you that the Newton's potential, which is this relation in any dimension, and so this is actually in n plus 2 dimensions, then this would be a relation. Actually, I'm mentioning this because later on I will use this when I make a connection with black hole, well, maybe a microscopic picture of what this black hole entropy is about. I mentioned already the Sitter space, so the Sitter space also has a horizon, and similarly it has an entropy and a temperature which is set by the Hubble scale. So the temperature for our universe is very low, extremely low. For a smaller universe like what people use in inflation, of course, it would be an important temperature, and this is, well, often used even in those settings. But I claim that even the way of thinking about the Sitter space at our cosmological time in this way may help understanding some issues about dark energy and even dark matter. So what I'll continue now is with ADS-CFT, where most of the studies have been done. Of course, I think most of you have seen this. What I want to illustrate here is that the duality which we have between gauge theory and gravity, where we think about the gravity theory as living in an additional space dimension extra than the gauge theory. The gauge theory lives on the boundary, and then there's gravity emerging in one extra dimension. The way it arises in string theory is by the familiar way in we can think about exchange of gravitons by closed strings and open strings stretching between objects that we call d-brane. If you do a quantum calculation of the open string, it's the same as an exchange of a graviton. This calculation shows, and actually also the calculations we'll do in ADS-CFT, that gravity seems to come from a quantum effect in the open string sector. Namely, it's a 0-point energy of fluctuations, I should say, of the open strings that give rise when you integrate them out to the gravitational force. It's basically like a Casimir force if you think about the virtual particles not being as particles but really being strings. And this already shows the emergence nature of gravity. I mean, I think once you understand this, when you have an emergent force that's a Casimir force, you're never going to go back to a fundamental description because you know that the degrees of freedom that are responsible for the force can also be excited. Like the electric fields that are between plates, they also can be excited and have an excited state. And the same is true for these open strings. And this is a different way of thinking about gravity. And there we'll see that this is indeed the main cause for deviation. So I will get there slowly. First, let me indeed mention then ADS-CFT as the example where we understand gravity in some form as being related to entanglement entropy. And the basic idea, and this goes back to Rio and Tagliani, is that the entanglement entropy associated to a region, actually usually we talk about a region on the boundary, but I will actually do similar steps that Rob Myers actually explained this morning, and actually also is due to his, one of his ideas, namely that this relation between entanglement entropy and the area can be understood really as an entanglement entropy between degrees of freedom in the bulk. And indeed, if you think about the degrees of freedom of the boundary, which is sort of this region, there is a way of representing those degrees of freedom as living in the bulk by applying what's called the renormalization group. You really think about putting degrees of freedom in each of these regions So these regions are regions of the size of the ADS curvature, and they contain a certain number of degrees of freedom. And if you then cut the space into two, you sort of break the entanglement between each region, and then the amount of entanglement is proportional to the length of this curve, or if it's the surface, it's the area of the surface, and this is what's expressed by this formula. Now this idea has now been used to put forward the proposal that space-time should be obtained by really entangling many qubits. So we have a large Hilbert space, and that the states that describe classical space-time have a high degree of entanglement, but that entanglement has this special property that it's proportional to the area. So you can certainly think then about this space-time as being sort of made out of qubits, where the qubits are like molecules, and the entanglement is like the molecular bonds that keeps them together. And the amount of entanglement is then set by the Planck scale, and so this is where the gravitational scale comes in. So this would be the starting point, and then you would like to derive gravity from something like a first law of thermodynamics for this. And these are the steps that people are making right now. An important point here, which I think was also mentioned this morning by Rob Myers, is that the states corresponding to space-time are actually very special states. They are states that have this high degree of entanglement, but they can be part of a much larger Hilbert space, where most of the states in the Hilbert space have no interpretation in terms of space-time. So if we want to build this Hilbert space, the states that we are interested in, the states that are also needed to explain this entanglement, we need many more states than the ones we can actually represent as genuine states in the separate classical space-time. And there's an important reason for that also in ADS-CFT already. This argument for the area law actually works only well when we have crossing many ADS regions. Locally, in very small regions, we don't really know how many degrees of freedom there are, because actually the number of degrees of freedom in each of these patches is finite, and this is determined by the curvature radius. So if you make the curvature radius very large, the number of degrees of freedom in space-time seems to go down. And it basically goes to zero. So this is an issue that we need to meet, and then we have to understand also this entanglement entropy. So entanglement entropy, here I remind you of the definition. You separate the space into two, and you take the trace over one of the regions, say on the outside, and then it's the trace of the density matrix that you obtain on region A, and then you express it in this form. And then we think that we can obtain gravity and also geometry from the entanglement entropy, where we have a large number of qubits. And this works well when this entanglement entropy grows like the area. And this we know in anti-de Sitter space. However, we don't fully know that area entanglement is actually very special. It's namely true for a ground state. If there are excitations, and these excitations may occur, for instance, near horizons where thermalization happens, and black holes in de Sitter, the question is, does this area entanglement still hold? And this is where we see sort of differences maybe appearing when we are really in situations where we have a finite temperature, like, as I said, with black holes, and also in de Sitter space. This assumption about the area law needs to be reconsidered. And indeed, one of the main points I'm going to make is that the ways that people have now been deriving Einstein's equations, and this is people that have been recently showing this, by a first law of thermodynamics applied to this idea, they look at the variations of this relation by putting an additional change of the state. And then the first law of thermodynamics seems to imply the linearized Einstein's equations, but it's assumed then that indeed the area entanglement law holds. So area entanglement and this derivation of Einstein's equations are directly related. Actually, area entanglement and holography is directly related because it also implies that you can express things on the boundary. So there's something that we put in right from the beginning, this law of area entanglement, but the question is, does it always hold? Now, what I'm going to do is actually making a proposal that's more general than what's happening in ADS-CFT. And the reason is that I want to indeed move to regions smaller than the ADS radius, and also want to go to de Sitter space. So the basic building blocks of space-time, I will call them stringy qubits. They're not ordinary qubits because we will see they will do something special. And let me call them S bits, because they're sort of stringy and they have some special properties. And one way I'm going to think about them is like the molecules that when I put them together are going to build space-time, and I'll call them monomers, because they're going to, as we see later on, make something more like polymers. Indeed, they're indistinguishable, and so there's a permutation group acting on them. And this permutation group will be important for understanding its properties. And in first instance, I'm going to assume very naive. Namely, I'm going to assume that the number of bits of these bits is going to be proportional to the volume. This seems wrong because it's not the area law, but let me just do it because this allows me at least to put degrees of freedom everywhere. And so I'm going to write this number, and I'm going to suggestively write it as C over 12. This is going to be the number of these basic bits, and it grows like the volume. The excitation energy of each bit, so the bit actually corresponds to a two-level system, or maybe more. I mean, I'm not that, not necessary to look at two-level systems, maybe three. But the important thing is that it has an excitation energy, which I call epsilon, where it has a negative ground state, and a positive energy state with energy plus epsilon. And I'm going to assume very naive that there's only one scale, firstly, in the problem, namely the Planck scale. So that means that both the volume V as well as this energy epsilon are set by the Planck scale. This would explain, by the way, the area entanglement that we have, namely that is set also by the Planck scale, but it does something very bad, which is well known. Namely, it creates a problem. Before I get to the problem, let me first tell you what the energy is. So I told you that the excitations have energy epsilon. So if I have a number of excitations, the energy will be proportional to epsilon. And there's this minus C over 12, which is sort of the ground state energy. If there are no excitations, every state is in the ground state, every bit is in the ground state, and this is this number. And the excitation energy epsilon just multiplies this number, and therefore I get a negative ground state energy proportional to the product. And you can see this has an energy density which is way too large, because everything is set by the Planck scale. So the problem occurs, which is the cosmological constant problem, that if I take these formulas, that I get a vacuum energy density. So this is the vacuum contribution. It's sort of like a Casimir contribution, and it's set by the Planck scale. And the energy density is the excitation energy divided by this volume per bit. And this is a huge number, and indeed it's 10 to the 20 orders of magnitude large. So I'm going to need a large number. And I'm going to take this large number to be 10 to the 60 for our universe, because I want to bring down this vacuum energy. Indeed, the correct value of the sort of observed vacuum energy would be a factor n squared smaller. So I'm going to want to reduce this vacuum energy by a factor n squared. And this you can do by, in this formula, by multiplying the volume here by n, and by dividing the energy by n, because then this goes down by n squared. If I look here at these formulas, this also does something to, well, here the epsilon becomes smaller, and the volume becomes larger, and that means the central charge, this number C, becomes smaller, and the delta becomes larger. So the solution to this, indeed, is what is called in string theory the long string phenomena. There's something that acts on these qubits, these S bits, namely permutation group, and they can form twisted states. And they can form twisted states of certain length n. And it's known in string theory that when you have twisted states, that the energy goes down, the excitation energy goes down, the central charge goes down, but the number of excitations, which sort of must give you the total energy, goes up. So we are multiplying the excitation number by n, and we are dividing the number of excitations, the number of degrees of freedom, by n. Now, in this new long string picture, which I call the polymers, we have a new ground state energy, and that energy is indeed n squared smaller, because C is n smaller, and the epsilon has also been n smaller, and so the ground state is the state with delta equals 0. But if you go back to the original value for delta, it actually is the energy difference between the original ground state and the new one. So the original ground state had minus c over 12, and this has 1 over n squared in front of it. And this is actually the energy of a operator that is the twist operator that combines in these n of these short bits in a long one. So this indeed is a way of not seeing all those bits in the space-time. I'm actually making the space-time degrees of freedom by combining many of these bits into a single one. And this reduces the number of degrees of freedom. Indeed, they will no longer grow like the volume. I'm going to introduce a new scale, and the n, namely, is the difference between, say, the Hubble scale and the Planck scale. And if you then work out what are the densities, you indeed get the correct value. So anti de Sitter space, and actually let me indeed do this, here, sorry, yeah. Anti de Sitter space corresponds to the state with delta equals 0. It's the ground state. It has a negative energy, and so these are the same formulas except I put delta to 0. And this is what I call the number of degrees of freedom. Now let me now work out what is the vacuum energy, because I just divide this by the volume, and I find that the vacuum energy is epsilon divided by nv squared. And this is what Einstein's cosmological constant would be. So the cosmological constant, which is determined by the ADS radius, is like 1 over L squared. And then the Einstein equations tell me that this should be the vacuum energy. And in what I call it's n plus 2 dimensions. I've sort of forgotten to tell you what n is. So n is, we're living here in not in n dimensions, but in n plus 2 dimensions. And then this is the correct value. So what I'm going to do now is make this correspondence such that I indeed choose a certain value for epsilon over n and n times v, so that this formula is satisfied. And you will see that this formula will work quite nicely. Actually, yeah, I'm going to use this relation later. Because indeed, if I take this equation, I find for CL when I put in this relation, this right-hand side. And we'll see why this is a nice value. So these are the values for epsilon and for, so epsilon is set by 1 over the ADS radius, and the volume is also set not by just by the Planck scale, but it also has the ADS scale in it. So this is the volume not of one monomer, but of n of them. So this is what I call the volume of a polymer. So that I put the relation up there now. Now I'm going to go to, so this was anti-de Sitter space, and it has the correct vacuum energy, but we want to go to de Sitter space. Now, how do I get to de Sitter space? Now I want a positive vacuum energy. So this is the same number, except with the plus sign. And so now I have to put in excitations. So I'm going to excite these same degrees of freedom by putting in a delta, which is non-zero. And the right value, well, you see here, the minus c over 12 must become plus c over 12, so delta must be cl over 6. And indeed, that gives you the correct vacuum. Now, note what I'm going to do is actually use these formulas to account for the correct entropy of our de Sitter space. De Sitter space has an entropy set by the area of the horizon, so the area with radius L. And with this formula here, when V is the volume of the space and A is the area, we find that this expression is equal to 4 pi CL over 12. Now, what is this microscopic origin? If I take this many bits with these excitation energies, and this is the number of degrees of freedom, we can start dividing all these excitations over all the available degrees of freedom. And this is counted by partitions. And a long time ago, the mathematicians Hardy and Ramanujan found a formula for counting partitions. Now it's also known as the Cardi formula, which is used in conformal field theory, but actually it's just a combinatorial problem of how to divide up integers in a number of boxes. So this is the number of boxes, and this is the number of integers, and you want to know how to divide them up so that the sum, you divide these integers in sums so that the total is equal to this. And then this is the number of integers. The number of different ways of doing this is counted by this formula. I think it has to be 4 pi. And with this formula, you get indeed the correct entropy, because if I take now delta L to be CL over 6, you find precisely the formula I had on the previous slide. Namely, this is going to be 4 pi CL over 12. As I said, the 2 pi should be 4 pi. So I have a way of counting the number of states by thinking about all ways of partitioning the excitations over all the available degrees of freedom. This is what describes the zeta space. So the zeta space is a excited state, and that's important. Black holes also have an entropy, and I'm going to do a similar counting for black holes. So I'm going to actually repeat these formulas, except that the length L, which is the length of the zeta radius, is now going to be replaced by the size of the black hole. So I've made the Planck scale orders of magnitudes larger by multiplying it by this factor n, which is indeed sort of thinking about the monomer making a long polymer chain. Now I'm going to do the same, but I'm going to do it only partially. So I'm going to do the same thing now for microscopic counting for black holes. The same kind of idea. I just take the original energy epsilon, but by some long string idea where the energy is reduced by a factor nr, I get some number of excitations. So I just divide up the mass in this fractional energy, and I do the same thing with my the number of degrees of freedom. Originally it was v over little v, capital P over v, but now I make this smaller by the same phenomena. And again, that's equal to the area of this region, and the counting goes the same. So compared to the zeta space, I've reduced the length of the chain. Namely, it's not the Hubble radius, it's some smaller distance, which is set by the radius r. And the energy, indeed, is also set by 1 over r. And that's sort of the natural energy scale for a black hole. But for the rest of the counting goes the same. The Cardy formula still applies. And indeed, the Cardy formula is a formula that multiplies this factor times that factor. But for black holes, this number and that number is again the same, because that's exactly the relation that puts us at the horizon. Namely, the ratio between those numbers is set by Newton's potential. So this is a way of thinking about Newton's potential. Basically tells you how many excitations I have on top of in these degrees of freedom. And when all of the degrees of freedom are excited, this is when I have the horizon. So it's a very natural way of thinking about it. Actually, this formula is not valid when this is smaller than 1. So it's only at the horizon that the entropy appears. And this is sort of a natural sort of consistency check of what I'm describing here. Now, this all seems very formal. But what I really want to do is sort of connect this to things we can test and we can look at. So first of all, I haven't told you anything about what really the degrees of freedom are. And here I already called them stringy qubits. And actually I've avoided using a lot of the technology and the machinery of string theory. But to tell you a little bit more about what is the microscopic description, let me do a little deep. Yes, go ahead. First of all, this counts how many states there are. And as you see, these are states that are made by combining many qubits over a very long region. So these are states that are hardly accessible to any local observer. Of course, we have states that we are associating to matter. These are not the degrees of freedom that describe matter. These are degrees of freedom that describe space-time. It will become a little more clear when I talk about the string theory language, because we have in string theory a very clear distinction between what we call matter excitations and what we are associating to space-time. The way we count black hole states is, as I just described, by using a formula like Cardy's formula. But this way of counting can only appear when we forget about the description in terms of particles living on space-time, because particles living on space-time only give a very minor contribution to the actual. Yes? Well, one thing that I might say here is that there is this relationship holds only when this is larger or equal than CL over 6. So that's the regime in which Cardy's formula applies. So de Sitter space is exactly where the equality is there. And what I expect is actually going on is that when you go below it, first of all, the entropy suddenly has to reduce. So suppose we started from a state which has indeed higher entropy than this one, where the delta is higher, and we are reducing the temperature. We end eventually up in this entropic state, and then we want to reduce it further. This cannot happen very easily because you have to get rid of this entropy. You get stuck in this state, and this is called a glassy state. So this is a glassy state which sort of has most of the entropy of the universe in it. It's 10 to the 120. If that compared to the entropy that we see, for instance, in the CMB, it's 30 orders of magnitude more. So this is where most of the entropy in the universe is sitting. And so we're living in a universe which is processing this many qubits at a scale which is the Hubble scale. And there's no way that we can see this happening because we're really like the smallest scales, and this is happening at a much larger scale. And this is decoupled from our own physics. So this is a long range. We have made many qubits string together, and this is where the things are happening. And the number of states is equal to the horizon area, but it's actually captured in the entire space-time, because the energy in this state is the dark energy. So let me tell you a little bit about the string theory language. Indeed, in string theory, we can exactly make models that do what I just described. In string theory, or better said, M theory, we have ways of building or counting black holes by using what are called D-zero brains. They describe excitations that are associated to the M theory circle, but they have a certain property, namely they are quantized in 1 over the radius also. And they are described by what is matrix quantum mechanics. The matrix has actually appeared because in string theory we have these open strings stretching between the D0 branes. And now the quantum mechanics has two kinds of branches. And this is where I have to indeed make the distinction between what we call particles and what we call space-time degrees of freedom, or excited space-time degrees of freedom. In the Coulomb branch, we think about these matrices as being commuting, and then the eigenvalues describe particle positions. This is how we reproduce ordinary particle mechanics. However, so in that sense, actually, we have to combine many of those D0 branes. The number of D0 branes is indeed equal to this number of excitations. But there's also a Higgs branch, and then we are looking at off-diagonal matrices. The matrices are no longer commuting. They can form the D0 branes then are no longer just ordinary particles. They can form things like D2 branes or membranes that move on this compactification manifold. So in M theory, in order to get in 4 dimensions, we use an extra manifold, which is usually Calabi-Yau, and a circle. This is the M theory circle. Then the D2 branes, they are like particles moving in this background on this manifold, and then can be other branes, that like particular D4 branes, that give rise to fluxes on this manifold. And then it turns out we can count how many states there are, because this manifold turns into a phase space where the symplectic form is determined by the number of D4 branes. And then the volume of this manifold, that's the central charge. This is the way that Strominger and Maldacena and Witten and later Strominger and Gaiotto and Yin sort of described a way of counting black hole states using a D0 quantum mechanics. But there are indeed these 2 branches, and it's in this Higgs branch where we have all of the entropy, because these D2 branes can capture these excitations. They can divide themselves over these many degrees of freedom, and this is how we reproduce the entropy by Cardy's formula. Indeed, this is sort of a well-known result. And it's this language where we have a distinction between particle or like objects, D0 branes. We have sort of membrane objects, which are the D2 branes, and then we have this Higgs branch where the things are being distributed over the entire number of degrees of freedom. This is where space-time ceases to exist, because we have no real picture, because we're doing this counting, first of all, using the internal manifold, and the original particles have no positions of the particles, for instance, are not visible anymore. In order to get particles, you have to get from this picture back to the Coulomb branch. Now, this may be a little technical. What I'm going to do is use this a little more in pictures. I call this the 2 phases of string theory. It's one that's sort of the vacuum phase where we have particles, and then there might be virtual open strings stretching between them. And it's these virtual open strings, when we integrate them out, that give rise to forces between them. Like gravity, but also other forces can be understood by integrating out these off-diagonal modes. So these describe the off-diagonal modes of the matrices, and these points are where we have combined a number of eigenvalues with each other. So they're localized excitations, and the off-diagonal modes, and that's very important, are in their vacuum state. In the Higgs branch, we have excited those off-diagonal modes, and they become part of a thermalized state with a very high entropy, which is due to the distribution of all these excitations over all these possible degrees of freedom. This is a picture of a heated number of degrees of freedom of space-time, and this is where the entropy is sitting. So when we form black holes, we form this phase, and we have to throw in matter, and there must be some way in which these two are interacting. So even though I've distinguished the Coulomb branch and the Higgs branch, there are regions where they are mixed, and when we have a mixed situation, part of the degrees of freedom are in an entropic state, and part of the degrees of freedom are just describing space-time with matter. This actually is what the anti-de Sitter space would look like. The Sitter space has certain degrees of freedom that look like this. But they're these long strings, so they're not really visible when you look at short distance. So indeed, I'm going to think about the Sitter space as an excited state with this entropy and this temperature. And it also has, besides an area entanglement, a volume contribution of entropy, because I can just apply the Cardi formula for every region, and you find that there's actually an entropy density associated to the space-time interval. So space is not empty, things are happening in there. And now it's going to be, the idea is that, how does gravity arise? Well, we're going to put matter in here, so those are localized excitations. They will, if there's area entanglement, they will lead to Einstein gravity. But with volume entanglement, something different happens. Because volume entanglement is really where you have a free energy or entropy density. If you're then changing the volume of space-time, you're changing the entropy density. And this is much more like an elastic force. What I'm going to show is that this assumption is going to change the way that gravity looks at long distances. Not at short distances, but at long distances. So the vacuum phase of string theory, we have entanglement entropy, and this obeys the area law, and this is well established now that this gives rise to, well, that this entanglement entropy happens in for instance, anti-de Sitter space. And so this indeed, I'll take this generally to be true in the vacuum state. But this is a vacuum state, and it's not the most generic state. When we have matter the matter in there, it changes the entanglement entropy, and it actually changes it by a certain amount that we can calculate. This is actually an approximate formula. The formula, it's determined indeed by this number of excitations. Anyway, the things that have been shown is that this change of entanglement entropy causes a back reaction. Namely, entanglement entropy is changing, but somehow this also induces a change of the area. And this is what gives rise to Einstein's equations, or at least the linearized equation. Actually, it's the first law that does this. And people like Myers and Van Armstrong have shown this. By the way, there's a relation indeed with Gauss's law, and this is one thing that was asked this morning by Gerard Hoofd. I mean, there's a way of thinking about the way how we describe gravity by Gauss's law. Namely, you can measure the mass by putting a sphere around it and integrating the Newton's potential. This applies in the vacuum phase. And this is where the entanglement entropy obeys an area law. The question is, does this still apply when we have other contributions? So now the main idea is that indeed at cosmological scales, the Sitter space is described by an entropic phase of string theory, but it has indeed these long strings and excitations that are set by the Hubble scale. It's a thermalized state with a very low temperature, but its entanglement entropy has an extra contribution that goes like the volume. And this actually is the way to write it down, and it actually has the Hubble parameter in it. So this changes the nature of gravity. It becomes actually more of an entropic force analogous to elasticity, actually elasticity appearing like in polymers. And what I'm going to do is indeed calculate now an effect that is due to this difference. Oh, I take a smaller region of size r. So this is a volume of size r. Normally you would say area entanglement is just this region, this formula, but if I multiply it with the radius of that region, I get something that goes like the volume. So the Hubble scale gives you the fraction of where the additional volume contribution comes from. So the area, which is usually measured in Planck units, now instead we have a volume measured where we combine the Planck scale with the Hubble scale. So there's an extra scale coming in the problem, which is the Hubble scale. I had it before, actually, I think. Really. It's the same equation I had before. So now I'm going to indeed put in matter, and this is going to change the response. I'm not going to put you through all the calculations, but I'm going to give you the general idea, and then I'm going to present you the formula. It changes the entanglement entropy, but it does indeed, at short scales, the Gauss law still holds, namely because their area entanglement is dominant. But at larger scales, the volume eventually takes over, because volume grows faster than area. And so there's still ordinary gravity at short scale. But when we are at longer distance scale, where we sort of see the entropic effect of the entropy in our universe, the volume and law of entanglement changes the nature of gravity. And it indeed, as I said, becomes analogous to elasticity. Also, I'm saying this is basically a summary. Yeah, actually this goes back to original questions I had. Let me indeed tell you the major points about what's the difference between the kind of gravity I'm looking at here and what we normally call gravity. If we think about the vacuum as a unique state, it has entanglement entropy. It has no real entropy because it's a unique state like a singlet state. If it has really entropy, like a thermal entropy, there are many possible states that this can occupy, and then we have to do a different kind of derivation, and indeed it can have a volume contribution. Indeed, I described the two phases of string theory where the vacuum, the Coulomb phase, really looks more like this, but the Higgs branch has more entropic. So ADS-CFT, everything is sort of caught in a unique state, but in the sitter space it's different. And actually horizons generally should be thought of as excited degrees, regions of space-time. And the dark energy is actually due to thermalization, where we start indeed breaking this state down and having many possible ground states. And now I'm going to indeed explain that dark matter, and actually I put a quotation mark because dark matter will not be matter. It's something that is changing the law of gravity, and it's going to be a memory effect caused by the volume contribution to the entanglement entropy. Now, what determines the scale of the dark, this dark matter effect? And here I sort of come back to the issue: what sets the scale of the entropy of the number of states that we have in our universe? It's the Hubble scale. And the quantum information is given by the de Sitter entropy, but we cannot access that quantum information. We really can sort of imagine now living in a big universe, which is like a quantum computer that's processing an enormous amount of states. A number of states equal to the area of the Hubble, of our de Sitter horizon. But we have no way of accessing those states because local perturbations are decoupled from it. This is the way that people try to build quantum computers, because they don't want the local disturbances to change the information. So something may happen in our universe without us knowing it. However, what would we see, and how would we know? And I claim that what we would see are the puzzling phenomena associated to dark energy and dark matter. There's actually a beautiful analogy, and it's indeed a polymer analogy. And this is a material called a polymer melt, where you put many of these polymers together and they entangle with each other. And they create an elasticity because once in a while they hold each other fixed. And it's in this context that people have calculated what are called memory effects. These polymers can leave the material and leave behind a strain in the system that doesn't relax immediately because there's a very slow dynamics going on. It's sort of an example of a glassy state. And this is a paper which indeed does the correct calculation. It's a calculation inspired by Duchenne, who basically told these people, well, if these polymers leave the material, they create an additional elastic force, namely they leave an empty space behind, and that will not be immediately released. There will be a strain in the system and I can calculate this, and here's the relevant calculation. I'm not going to show you the details because I haven't published it yet, so I'm not going to give away everything. But the analogy is going to be clear. I mean, the temperature of the system is like the energy scale that I have, and it's actually the Sitter scale, the Sitter temperature. The volume is going to be, and this is actually here explained in here. There's some number which is called the entanglement, where we take this many monomers, and then we build from the little volume, the volume of the polymer, which is dE n times d0, exactly as I did in the calculation. They then calculate the displacement due to removing one of those, and this gives rise to an additional elastic energy, and the calculation is down here, and this is the calculation I will do. And actually this formula, you multiply the Young modulus with the change in displacement, and actually I'll show this calculation on the next slide. What do you do with elasticity? You remove a certain volume, and then the system displaces a little bit. So we are here in an entropic phase where I remove some entropy from the system or some volume, and then it has to react by elasticity. Namely, what it does, it displaces by a volume which is equal to the removed volume, V0. So this is the area A, and the displacement times this area is equal to this volume. Now you can do a simple calculation and calculate this quantity, which is the strain in the system. It's proportional to this volume that has just been removed, and with some prefactors that depend on the dimension. And actually these prefactors will help me explaining some phenomenological relations. If I have more of them, they actually just become linear in the number that I've removed. Namely, because the force law goes like 1 over, so the displacement goes like 1 over A, the force law goes like 1 over A, well, the volume. So this is the difference between elasticity and gravity. Gravity would put not a 1 over A here. This is like Newton's potential, but it has a 1 over R law, not a 1 over R squared law. Elasticity has 1 over R squared. So this actually is then giving us an additional component in the gravitation, in the elastic energy in this case, but this will translate to gravitational energy in a minute. So now I'm ready to present a comparison. So what I'm going to show you now is that there's an effect that I'm going to explain, namely it's the effect due to dark matter. In particular, this effect in galaxies, which has been well studied. We have ordinary matter, so these are the matters that we normally know about and described by Newton's gravity. But if we take the matter that we see, we know that we don't explain how these stars are rotating. What is being observed is that the stars rotate much faster. So this is expected in terms of what the visible matter would be, including the gas and the stars, and this is what's being observed. And the difference is generally attributed to dark matter. There are other ways of seeing dark matter with gravitational lensing, either directly or in terms of weak lensing. And here you see indeed regions with matter that has no other cause than just, well, there's no regular ordinary matter visible. So it should be dark matter. Now what I'm going to do is actually derive a relationship between the Newton potential. So what I wrote down here is actually the observed velocity as a function of distance, where I separated it in terms of baryonic contribution, which is due to the visible matter, and a dark matter contribution, which should be the difference between those two. So the baryons would go down this way, but what's observed is some flattening, where the velocity as a function of distance becomes roughly constant. Now, there is already a hint that this has something to do with the cosmological scale. And this is observed by, well, maybe I should first explain that. It's namely observed in the relationship between the velocity that you see far out and the amount of baryonic matter inside the galaxy. It's quite a magical relation because the amount of baryonic matter is about 1/30th of the total amount of matter in the galaxy. But it determines the velocity far out. Namely, the relationship that seems to work is that if you take v squared over r squared, so that's total has a v to the 4th in here, it goes like the acceleration only due to the baryons times a scale set by the Hubble scale. This is called, I call it Mond phenomenology because it's sort of a fitting parameter that seems to work very well. A fitting equation that works very well. I'm not going to tell you that I'm going to derive the Mond assumption, namely that we really have to change Newton's law. No, there's some way that the phenomenology will appear. And here it's also visible as follows. Here's plotted the amount of visible matter we have in stars and gas. This is the velocity that is being observed out here. And it's a log-log plot, so the slope here seems to put a 4 in here, plus, a number in front that tells you what the proportionality constant is. And that gives you this number. This is another way of representing the same data. Here you compare indeed the velocity squared divided by what you expect by the baryons, which is the right-hand side, and you compare that to Newton's acceleration, and you get this nice relation. This relationship follows from a formula, and the formula that I derived is this. It's indeed a formula very similar to the what I had for the elasticity. It's an expression for the amount of, I call it gravitational energy, because if you take the square of the acceleration and you integrate it over volume, it's like integrating E squared over volume, and I divide by 1/4 pi b. And this is determined by the amount of information, basically the amount of entanglement that I've removed due to the matter. And here I have the scale, and actually the number 6 I can reproduce. And this is a relationship. When you differentiate it with respect to R, gives you the phenomenology that we've just seen, except in that case I have to keep R here constant. And that's quite an important difference between what I do and what the Mond people do. This is another way of writing the same relation. It actually gives you a relationship with the amount of dark matter and the amount of baryonic matter. And what I can do now is derive what is being observed. I can calculate the density of dark matter and the density of and compare it to what's seen in baryonic matter. Of course, I already told you I reproduce the Mond phenomenology. So all the checks that people have done using the Mond idea are curves like this. There are hundreds of them, and they work very well with basically no free parameter, because once you've sort of calculated the constant, the formula is fixed, and you can basically fit many galaxy curves, and it's quite impressive because this is not being challenged by the ordinary particle dark matter, which needs about at least 2 parameters for every galaxy in order to be able to fit those. There are also regions where Mond doesn't work very well. And actually, this is where the difference which I have and what Mond has is important. Mond has a relationship when if I differentiate with respect to R, I would keep this thing constant. This is not true in clusters, for instance, because there the matter continues to increase as a function of the radius. If you calculate this formula and compare it to cluster data, you get this. So this is actually a paper where people looked at the coma cluster and first figured out that Mond doesn't work. One needs about a factor of 4 larger, and this factor of 4 can be understood quite well. Actually, I did leave, I'm not sure I put in that slide. So this is the amount of matter you see. This is the amount of matter that Mond would need in order to explain the observed curve. So this is sort of a paper that points out Mond fails in clusters. This is what I can do with my formula. If I assume this matter, and this is the amount of stars that sort of was left out here, this is what Mond would need. Clearly, it's more than what I have here, because even if you take this is logarithmic, you can add those up, but you'll never get a good curve. But I can explain this curve with the equation. So I think that's pretty good, and I have some more fits that seem to work very well. What about the cosmic density? Actually, here I have a formula. Actually, I have not shown that one. Actually, I have from the same formula which I have here. I can derive indeed the relationship between the baryonic density and the dark matter density in terms of the Hubble scale, and I can extend this to the size of the universe. I get this. This is the relationship I get. And this is what's being observed. So I have one formula, I can do clusters, galaxies, and also reproduce this. And even the same relationship, which is the one between dark matter and baryonic matter, seems to hold when you evolve it in time. So I think this is quite a challenge sort of to deny this kind of formulas. I mean, there's some agreement between the formula and what is being observed. And I think I've provided you with a conceptual, at least, understanding of what might be going on. Thank you.
Okay, questions?
Well, I just want to ask for more clarification. I'm a big fan of MOND, and I worked a lot on it, but I gave it up because I couldn't get the cluster scales to work out right. So what exactly is do you mind repeating and going into more detail, what exactly is the physics that makes the clusters work?
If I assume, so when I derive the MOND equation, I said I differentiate with respect to R, assuming M to be constant. Then I differentiate only this R. But suppose I have a matter density. Then M would go like R cubed, if it's a constant density. If you then differentiate with respect to R, you get the same relation with the factor of 4. That's the factor of 4 that's mentioned here. So I can, with this relation, I can explain the difference. You really get you get an enhanced, the reason that there's a big difference. In galaxies, most of the matter is in the center and then it falls off. Yeah. But in clusters, most of the matter is contained in X-ray emitting gas. And that gas keeps growing until the far edges of the cluster. I know there's a slope. So what I put in is a slope. And actually you can derive the slope from this relation. You see the slope is put in from here. So here I put, you can derive the slope parameter, so from the slope you can determine what the enhancement factor is. And there's an enhancement that indeed for constant density would be a factor of 4. But if it would be like 1 over R cubed, it's actually the 1. So there's anything in between gives you some factor. And that seems to enhance this.
I have another question about clusters. What about the bullet clusters collision? Can you say something about?
I told you that the dynamics is a memory effect which is associated with the flow dynamics of the underlying system. So there is no direct law. So what I don't have like MOND people say there is a modification of the acceleration that should be a direct response to where the baryonic matter is sitting and what you see in terms of the acceleration. I'm saying this is an effect that determines sort of the geometry of space-time, but at the slow dynamics, which is, so the equation I wrote down is where I assumed relaxation to happen over a long time scale. What happens in the bullet cluster is that things are colliding, and there, whatever effect was responsible for the dark matter doesn't immediately react to what's happening to the baryonic matter. It just may continue. So there is ways in which this is essentially different from the MOND description. I'm not trying to find a law that, actually I could even say, I put assumptions in deriving the equation. So there are situations where these assumptions may break down, and therefore you have to study dynamical issues like in the MOND, in the bullet cluster, in order to really have a description of that one. So the relationship doesn't even hold because the assumptions that I made in deriving it would break down. Yes? Oh, sorry, here.
Let's...
How do you explain, do you have any explanation for this number 10 to the 60 that suddenly appeared at the beginning?
The number 10 to the 60 has to do with the amount of information that we have in our universe. So somewhere we need a large number. And I think what I had to assume is that we have a certain amount of entropy in our universe, which is 10 to the 120, and that is given to us, and that's the number of states we have to deal with. And this is what sets the scale of the cosmological constant. So it is not something that, so I think physics doesn't need to have one scale. If it has large numbers, you already have more than one scale. So I don't think that the number 10 to the 60 can be calculated. It's one of the parameters that you have to put in. It's a difference between the cosmological scale and the Planck scale. It's like what people have to do in these polymer models. The polymer has a certain length, and there's a size of the monomer. And whatever the length is what makes our universe. So I think it has to do with the degree of the length of the entanglement chains that we have been forming in order to sort of get our degrees of freedom. That makes space-time. But this large number, I think, is an input and cannot be sort of calculated independently.
So I was just going to ask, it seems like there's an opportunity for your theory to make a prediction about dark matter in addition to these postdictions. So I just wonder what you think about the following. So cold dark matter predicts that like a big galaxy halo like our Milky Way galaxy halo is full of a lot of small subhalos that formed much earlier in the history of the universe and just persisted. They got eaten up by our larger halo later on, and nothing's been able to strip them apart. But that hasn't been observationally tested. But in about a year or two, this telescope ALMA will be able to really make a good test of whether those subhalos are really there or not. I wonder what you think about it in your approach. Should they be there or not?
The usual way in which this is done is that people assume that the dark matter forms the structure first, that the baryonic matter will follow it, and it does so in a hierarchical way. And this is how these subhalos form. And clearly, this mechanism is different. And I think the formation history, we really have to go back to what we think our theory of structure formation is, at least in what is the order in which things happen. So I know there are many ways in which dark matter is being used. What I can reproduce is the additional gravitational wealth that we need to explain structure formation, but whether it happens in the same form, I don't know, because what you're telling me is that the way that dark matter forms these halos is by a particle dynamic. And this is clearly not what's happening here. So, and it's somewhat related to the other question. This has to do with dynamical issues that I've not fully described, because I've written down an equation that is like an equation in a quasi-static situation. I've not studied what the sort of dynamical equation is that we should use for dark matter, which is sort of the question you were asking me about. So anyway, I don't think, for me, the problem that the particle dark matter has is, of me, a strong reason to believe that things like this might actually solve those things.
So the number 10 to the 60 corresponds to the Hubble scale right now in Planck units. But at earlier times, the Hubble scale as a distance was much shorter. So is it a coincidence that it agrees now, or are you going to have different physics, different cosmological constant at earlier and later times?
So one thing that I showed here is that the relationship I find sort of seems to work quite well in the cosmological evolution. But I have actually another answer to this. I mean, when I try to change... So I'm thinking that the gravitational laws, as we are using them now by Einstein gravity, need to be modified at these scales. I mean, the fact that we are forgetting the 10 to the 20 entropy or whatever, or degrees of freedom that are associated with dark energy. The dark energy has a very large number of states, a very large phase space that nowhere in our present cosmological picture plays a role. I think we have not fully understood the evolution equation. So I even question that our usual way we think about the cosmological evolution can be fully extended to the degree that we are doing it currently. So I first have to see what's going on when we develop this theory further, how the cosmological evolution equations will be written down in this way.
I mean, so I think that fitting rotation curves and all of these things with dark matter is all well and good, but the most precise and convincing evidence that we have for dark matter is the silk damping tail of the CMB, and that is something that
I'm not hearing you well.
Sorry, the silk damping tail of the CMB is the most precise and convincing evidence that we have for dark matter, in my view. And MOND has a problem fitting this. And so like the way to state that is that whatever is causing structure, giving you extra matter, has to be forming structure hierarchically on scales larger than a megaparsec on timescales of order matter radiation equality. Or the large-scale structure in galaxy surveys and the silk damping tail of the CMB will be wrong. So, I mean, I think that's like the zeroth order thing that you need, that when it comes to dynamics that needs to be checked before you go to rotation curves or anything like that. Like these are all nonlinear environments. Linear structure formation, megaparsecs, timescale of matter radiation equality. And MOND doesn't do that, and you need to jump through hoops to make it work.
Let me make two comments. I mean, I've not indeed included how I would describe the CMB and what the current explanation is using dark matter. But this is dark matter worked out in a certain model that indeed describes the large-scale structure much larger than the scales I've been looking at here. And indeed, the usual way people talk about this region is this is where the non-linearity of gravity becomes important, where baryonic feedback comes in, so it's a complicated one. However, there are certainly things we don't understand there, and I don't think that extrapolating the laws of physics that we have derived at our scale to the cosmological scale and forgetting about all of the problems that we have in these intermediate scales is a valid approach. And so I'm actually quite also impressed with the number of data that have been verified using the MOND relationship. If you look at the number of plots, the number of points that people have checked compared to the CMB data, I think there's much more data that seems to confirm the MOND idea than well, I mean, of course we have to explain the CMB data, but I think the challenge is still to see what the MOND phenomenology can be, how should I say it? It cannot be ignored, even from the people that think about ordinary particle-like matter.
Erik, I just want to support you because you went right by what I think is the most convincing answer to what was the challenge that was just given. The baryonic Tully-Fisher relation, and the fact that the Tully-Fisher relation sharpens up strongly for baryonic matter as opposed to total matter, is very hard to understand in a particle dark matter perspective. As well as, just to repeat what you just said, all of the rotation curves and those hundreds of plots working out precisely with no parameters fitting them. David, that really is something which I think that the people who think dark matter is the right explanation really have underestimated and gone right by.
So, next question. Around the corner for me.
So just a comment about the baryonic Tully-Fisher relation. So it's true that MOND does a pretty good job of explaining some of this data. On the other hand, there have been recent simulations where you include proper baryonic feedback that have done an equally good job of explaining the baryonic Tully-Fisher relationship, including dark matter and baryons. Because most of the original comparisons only included simulations where you have purely collisionless dark matter and you don't include baryons, which play a very important role in nonlinear evolution.
I'm familiar with these things, but I also know the way that goes. The uncertainty that there is in the models has to do with how fast do you form supernova, star formation, all those things, all kinds of parameters that you can put into the simulation. And what people have been doing is tuning their dials in such a way that they can get the relationship out. It doesn't mean that you have explained the relationship, but simply you have been able to put your parameters in such a way that these relationships come out. So I agree, maybe the Tully-Fisher relation is not a direct contradiction yet with particle dark matter, but the explanation that is given from that point of view is very unnatural because the mechanisms that play a role have to do with baryonic feedback, which is different for every galaxy. I mean, how many stars are being formed, how many supernovae, it's every time different, yet they lie exactly on the same relationship. And I don't think that the baryonic for a particle dark matter explanation is actually believable in that context.
Okay, are there any more questions? Okay, then let's thank the speaker again.